So in this class, we're going to discover rules for finding antiderivatives of certain elementary functions. These rules will be ones that we use repeatedly over the next couple of months. So we know that this integral represents an area, the integral from 1 to 3 of 8x cubed dx. So I'm going to shade the relevant area in this picture of 8x cubed, y equals 8x cubed. So the bounds are 1 to 3. So here's 1 and 3, and I'm looking for the area underneath this curve. We can approximate that value, the area under the curve, on a graphing calculator. But let's try to do it by hand using the fundamental theorem of calculus. Okay, fundamental theorem of calculus says that if you're integrating from a to b a derivative function, f prime of x dx, that it's equal to f of b minus f of a, where f is the original function, f is a function whose derivative is f prime. So in this example, the integral from 1 to 3 of 8x cubed dx is f of 3 minus f of 1, where f is some function whose derivative is 8x cubed. So if I can come up with a function whose derivative is 8x cubed, I can finish this problem. Okay, so a function whose derivative is 8x cubed. Well, what's the exponent have to be? Oh, yes, x to the 4th, and you got the 2. Good. Yeah, so the derivative is going to be the antiderivative. The exponent has to be 4. And when I bring that 4 down and multiply by whatever's here, I need it to come out to 8. Okay, so it must be that that's a 2. So that when you bring the 4 down, 4 times 2 is 8, and then you reduce the exponent by 1, you get 8x cubed for the derivative. All right, I'm going to choose a specific value for plus c. Let's do plus 5. That function is an antiderivative of 8x cubed. Its derivative is 8x cubed. All right, so to put it all together, I have the integral from 1 to 3 of 8x cubed dx. That should be f of 3 minus f of 1. I'm going to use a new notation. F is 2x to the 4th plus 5. So this is going to be 2x to the 4th plus 5. And then I need to evaluate that at 1 and at 3. And I'm going to subtract the 2. So first I'm going to plug in a 3. So I get 2 times 3 to the 4th plus 5. And then I'm going to plug in a 1. 2 times 1 to the 4th plus 5. Simplify each of these, and then I'm going to subtract them. So 3 to the 4th, what's that? 81? 81 times 2 is 162. Plus 5 is 167. And then 1 to the 4th is 1, so that's 2 plus 5 is 7. And I get 160. So this new notation means plug in the top number and subtract whatever you get when you plug in the bottom number. This vertical line with a 1 and a 3. So also notice that the value we chose for c doesn't matter. Like if I had done 2x to the 4th plus, I don't know, pick another one, 8. I think I'll still get 160. So if I make that an 8, make these 8s. So this is going to be 162 plus 8 is 170. And then 2 plus 8 is 10. Still get 160. And you'll see it's because we have plus 8 and then minus 8. So whatever you chose for plus c, they just always are going to cancel. You're going to have a positive 1, and then you're going to subtract it. So in the future, we're not going to bother using a plus c. Pick the easiest one, which would be 0, when we're doing definite integrals. Since finding antiderivatives is tied to evaluating definite integrals, we use integral notation if we just mean what's the antiderivative. So this integral without bounds on it of 8x cubed dx is equal to 2x to the fourth plus c. It just means find the antiderivative. The process of finding an antiderivative is called integrating. So I want to integrate, find the integral of 2x plus 3 dx. So I need a function whose derivative is 2x, x squared. And then I need a function whose derivative is 3x, and then I need a plus c, plus an arbitrary constant. All right, when the integral sign doesn't have any limits of integration on it, the integral is called an indefinite integral, as opposed to a definite integral, which has limits on the integral sign. The dx is a necessary piece of every integral. Note that it always goes to the far right. And for indefinite integrals, the plus c is mandatory. Okay? Omitting the plus c will cost you points. C for cost you points. Finding antiderivatives is going to be important for us for the whole semester. So how do we do it? So we're just going to reverse some of the differentiation rules that we have right now. So some of the basic antiderivatives. So the integral of x to a power, we're going to reverse the power rule. I need to increase the exponent by 1, and I need to undo the derivative. So if I were to take the derivative of x to the n plus 1, you'd bring the n plus 1 down, and you'd have n plus 1 times x to the n. But I don't want an n plus 1 in front. The thing in front is a 1. I need it to cancel, so it's going to be 1 over n plus 1 times x to the n plus 1. So in words, increase the exponent by 1, divide by the new exponent. Okay, and the integral of 1 over x dx, an antiderivative of 1 over x. So a function whose derivative is 1 over x, ln x. Oops, and I always need plus c's on all of these. There's like a super technical reason that I put absolute value bars on the x there, on the ln of x. So you can see me outside of class if you're interested in why. You won't lose points if you omit the absolute value bars. But I'm going to put them there so that I'm not lying to you. Okay, so a few more. A function whose derivative is e to the x. E to the x plus c. A function whose derivative is cosine x. Close. It wasn't the plus c. Function whose derivative is cosine. Sine of x, yeah. A function whose derivative is a to the x. All right, what was the derivative rule for a to the x? Anybody remember? Yes, that's the derivative rule, a to the x times the ln of a. So if I want to undo the derivative rule, instead of multiplying by ln a, I'm going to divide by it. So this is going to be a to the x over the ln of a plus c. Okay, an antiderivative of sine of x, a function whose derivative is sine. Now use your response with the negative, right? Function whose derivative is sine, negative cosine. Because the derivative of cosine is negative sine, so we need that extra negative. All right, if you want to take an integral of a sum or a difference, you can do it term by term. So you can take the integral of f of x dx and plus or minus the integral of g of x dx. So that just allows you to go term by term, finding antiderivatives. And then a handy little rule is that if you're taking the integral of a constant times a function, you can pull the constant right out of the integral. So this is c times the integral of fx dx. All right, so that was a lot of rules all at once. Let's use some of them in some problems. Okay, an antiderivative of 8x cubed dx. So I'm going to write out more work than you may want to, and that's okay, but I just want to like show all the steps to start out here. So I'm going to pull the 8 outside of the integral. That's one of the rules that I'm allowed to do. If you have a constant in front of your function, you can pull it right out. And then my rule for powers says increase the exponent by 1 and divide by the new exponent. And then just to simplify, 8 over 4 simplifies to 2x to the 4th plus c. All right, for the next one, I'm going to do some fancy algebra before I start trying to find antiderivatives. So first, this is a difference, so I'm going to break this into two integrals. So this is going to be the integral of 2/5 e to the x dx minus the integral of x minus 1 over root x dx. I'm going to take this constant 2/5 and pull it out of the integral. I'm going to do two things at once here. First, I'm going to put my square root of x under each piece of the numerator. I'm going to break that into two fractions. And I'm going to rewrite square root of x as x to the 1/2. So this is going to be the integral of x over x to the 1/2 minus 1 over x to the 1/2 dx. Okay, I'm not doing anything to this first piece yet. Now I have an integral of another difference. I'm going to break it into two integrals, and I'm going to reduce each of these fractions as I go. So this is going to be minus the integral x to the first over x to the 1/2 reduces to x to the 1/2. Just subtract the exponents. And then this is going to become plus because I'm distributing the negative sign. The integral of x to the negative 1/2 dx. Now I have broken this up into three integrals that are relatively easy. E to the x antiderivative is just e to the x. This is a power rule, so I'm going to increase the exponent by 1. So 1/2 plus 1 is 3/2. And I'm going to divide by the new exponent, which is 3/2. But dividing by 3/2 is the same as multiplying by 2/3. So I'm going to do that instead. Then I have x to the negative 1/2. Add 1 and you get positive 1/2. But then I need to divide by the new exponent. But dividing by 1/2 is the same as multiplying by 2. And then I have a big plus c on the end. And we should be able to check our work by taking a quick derivative of the result. It should give us the original integrand back. Or something algebraically equivalent to it. So I broke up this fraction to x over root x minus 1 over root x. Because now these are just two fractions with the same denominator. So you could, so I sort of unadded these two fractions. So there's a lot of integrals we can do just by being able to reverse our derivative formulas. But there's still a lot of integrals we can't do. Products, compositions, and similar type things. It's hard to undo. So we can do a lot more stuff now than we could yesterday, but there's still a lot to learn. Okay, so that's it for the demo. You guys can start on the activities. Put up a flag if you have a question.